Have a great day. Welcome to the Control System lecture series. In this fifth lecture, we will learn the modeling of mechanical system elements. So before going in this lecture, let us have a brief review of first lecture. In the first lecture, we have learned there are three steps to get any system. First one is mathematical modeling, second one is analyzing, third one is designing. So why mathematical modeling? Because this modeling gives us very gives us opportunity to analyze very easily, and that may be in the time domain analysis or frequency domain analysis. And this mathematical modeling is normally represented by differential equation, and that differential equation can be transformed using Laplace transform. So that are very easy to get the mathematical modeling. If modeling is okay, then we moves towards the analyzing, and in analyzing we found that all the parameters are desired output is as per specified requirement. Then we will move towards the design, and in the design we design the prototype modeling. Before prototype modeling we design a system, and based on the design parameter or design specification, if it is okay, then we will develop a prototype model, and if it is okay, then we will move towards the design of actual item or device or system. If not found okay, then we will moves back towards the remodeling, reanalyzing, and again designing. So let us move towards the modeling of mechanical system elements. So any mechanical system, any control system or system can consist of a mechanical component as well as electrical component, and that may also have a hydraulic and pneumatic elements. So in a mechanical system, there may be three types of the motion that takes place. First one is translational, second one is rotational, and third one is a combinational. In a combinational motion, basically it may consist of a translational as well as rotational. Translational may be cause, and rotational its effect, or rotational may be cause, translational is effect. So that have a large application of the combinational motion. In a translational motion, what happens actually? Translation motion takes place in the straight line, and in this there may be displacement, velocity, and acceleration. So before moving towards, let us review the Newton's law of motion, which states that the algebraic sum of forces on any rigid body in a given direction will be equal to the product of mass. Here you can see product of mass and its acceleration in the given direction. So it will represents the force, and in the mechanical system the mass is considered to be storing its kinetic energy. So it will be analogous to the inductance of the electric circuit or network. So as we know that mass may be W by G. So here in this diagram you can see that this is the mass, this is the mass that is moving towards this direction uh, due to this applied force F. So this applied force will be equal to product of this mass and its acceleration in this direction. So here you can write the force will be equal to mass into acceleration with time. So R you can write m d square xt upon dt square, or in terms of the velocity m dv by dt. So this is representing the force mass system. Second one is a linear spring, and this may be actual spring or a cable or a belt, and basically it stores the potential energy, and it is analogous to the capacitor in the network. So in electrical system we know that there are two uh, devices or elements that stores the energy. First one is a inductor, second one is a capacitor. So, and these two are analogous to the mass and linear spring in the mechanical system. Now here in this spring, you can see this is the spring, and the force applied in this spring is in this direction. So due to this force, there will be the motion in the spring, and that is called displacement, and this displacement and this product of this spring cost will represent the force Ft. So this force is causing the movement in the spring in this direction, a movement of x, and its spring constant and its unit is Newton per meter. Now if we consider this spring is a preloaded with the tension T, then the actual force required will be Ft minus T will be equal to kxt. So since a spring is preloaded, so we need to apply less force compared to the earlier. Now if a motion takes place, so definitely there will be some resistance that will oppose to this motion. So these resistances are called frictional forces, and that forces are in general non-linear in nature, but here we are considering a linear up to extent. So there will be three types of the frictional forces that will appear in any mechanical system. First one is, you can see, viscous friction, second one is static friction, and third one is a Columbus friction. So let us go to the viscous friction. So what is viscous friction? Viscous friction is a retarding force, so like a resistance in a electric circuit. So here it is a retarding force that have a linear relationship between the applied force and its velocity. Velocity is dx t upon dt. So this is a linear relationship between the force. So here B is a viscous friction coefficient, and so Ft equal to B dxt upon dt. So here this is a dash spot, and in this dash spot the applied force is F. Applied force is F. In this direction there will be the displacement of x. So this dash spot, in the dash spot there will be viscous friction, since there may be viscous friction maybe between the liquid or gas, or between the liquid means here a greasing or some lubricating oil is filled, so that will appear between the moment of this piston and this force. So there will be the viscous friction in this. So this viscous friction, as we know, that can be represented as a Ft equal to B dxt upon dt. Now, static friction. If anybody wants to change its the position from static to the dynamic, what happens? There will be retarding force that will prevent its motion from the beginning. So Ft equal to, that will be plus minus Fs xt dash means dx upon dt equal to 0. So this force will appear only in the state of the stationary, when the system when the body is stationary. Once a body starts moving, this force disappears. So but the direction may take place, and if may take place means, if it is in static, the force direction will be different to the earlier. If it is in dynamic, then it will uh, force to stop it. So that is the static friction. Now, Columbus friction. So Columbus friction takes place between two surfaces. So here it is also a retarding force similar to the resistance in a electric circuit, and it is a constant amplitude with respect to the change in its velocity dyt upon dt, or dxt upon dt, dxt upon dt, divided by dy upon dt, sorry, dx dt into fc. So if the displacement is x, so that can be written as a fc dx upon dt upon mod of dx upon dt. Or if displacement is y, then dyt upon dt, dyt upon dt mod into fc, where fc is a Columbus friction. So basically you can see there are three types of frictional forces appear in the mechanical system. First one is the viscous friction, second one is a static friction, third one is a Columbus friction. Now, rotational motion in a in mechanical system. So rotational motion can be defined as a motion about the fixed axis, if it around a fixed axis. So here there is also a Newton law of motion for the rotational system. So here algebraic sum of moment or torque about a fixed axis will be equal to the product of the inertia and angular acceleration about a axis. So here you can see this torque will be equal to the J into alpha, J into alpha, where T is a torque in Newton meter, J is a inertia of the body, that is kilogram meter, alpha is a angular acceleration in radian per second square. So first is similar to the mass in a translation motion. In a rotational system, there is a inertia, and basically it is a property of the element that stores the kinetic energy of a rotational motion. So this depends upon the composition, geometry, and its density and axis of rotation. So here you can see this body has a circular disc, has a inertia J. The torque is in a say clockwise, then there will be displacement is also in a clockwise theta. So this is the torque inertia system. Now second thing is that, and in this disk the inertia will be half mr square. So torque equation can be represented as it, since that will be equal to inertia into angular acceleration. So j into alpha t, or you can write j d omega t upon dt, where omega is a angular velocity, while or j d square theta t upon theta dt square, where theta t is a angular displacement in radian. So similar to the spring in a translation motion, there is a torsional spring, and it springs works by twisting its axis, uh, twisting its end along its axis. It stores the mechanical energy. Basically, it stores the potential energy, and the torque exerts, the motion will happen in the opposite direction. So here torque developed in the spring due to the applied force, there will be, that will be equal to k into theta t. So where k is a spring constant or torsional spring constant, its unit is Newton meter per radian. And if this torsional spring is preloaded with the torque Tp, then the required torque in this will be lesser compared to the earlier, means Tt minus Tp equal to k theta t. So this is similar to the linear spring in the translational motion. Now in the rotational motion of mechanical body, there will also be a viscous friction, static friction, and Columbus friction. So viscous friction in this is a resistance to the torque. Basically, it is a retarding torque, and it also here it is also have a linear relationship between the applied voltage and angular velocity. So Tt is equal to b d theta upon dt, or omega t. Tt equal to b into omega t. So where B is a viscous friction coefficient in Newton meter per radian per second. Theta is a angular displacement in radian, and torque is in Newton meter. Second type of friction in this rotational motion is a static friction, and this is also a retarding torque in a rotational system. So it prevents rotation from the beginning. So here Tt equal to plus minus Fs, you can mod up at theta s equal to theta dash equal to 0. So this friction will exist only when the body is stationary, and it will not be present if the movement takes place. Coulomb friction or Columbus friction. So it is similar to the translation motion. It is a here it is a retarding torque. There was a retarding force. So in this case it is a retarding torque. It is a constant amplitude with respect to change of the angular velocity. So angular velocity can be, RTT will be equal to Fc omega uh, by mod of omega, or f equal to d theta t upon dt mod of d theta t upon dt, where fc is a Columbus friction coefficient. So now coming to the three example of the combinational motion. First one is a belt pulley arrangement. So here there you can see in this direction, in this diagram, this is the pulley 1 and this is a pulley 2. So pulley 1 and 2 are connected through a belt arrangement. So this belt arrangement, and at the pulley 1 there is a drive or motor that moves or runs this pulley. Due to the moment of this pulley, since this pulley will also move because this is connected through the belt, and on this belt you can see there is a weight W. So this weight will have a translational motion. So pulley have a rotational motion while weight has a translational motion. So in this way, a body can be displaced from one position to say position 1 to position 2 can be displacement. So if displacement is xt, so now you have a theta t, xt, tt means torque developed by motor, weight. So you can write the differential equation for this system. So normally this type of arrangement you can find in a colliery where coal handling is take place, or in power plant where the you can see the movement of the coal from the storage point to the boiler point, near the boiler point, or from the mines to the place of dumping, that is through this pulley belt arrangement. Second one is pinion rack arrangement. So here this is the pinion. You can see this is the pinion. You can see, and it is moving in this direction due to the drive motor. Basically in these are the induction motor that is used to move this. So this pinion is attached to this rack, and if the movement of the pinion takes place in this direction, then the rack will be this way. So this will be moving the rack, and then the body placed on this rack, say it is at position here, have a weight of W. So this will move in this direction, and finally it will be here. So it can take place. The moment of the body can take place, and this displacement is xc. So you have it xt, theta t, tt. So that can be very easily represented in a mathematical expression. And another arrangement of this you can see also, not for using the cutting of the wood in a uh, board cutting mill. So in the board cutting mill, here you can find a blade at this position, and if the body moved, then that wood would be cut it into pieces. So this is the another example. And third one is a lead screw mechanism. Here also rotatory to linear motion. So here motor rotates and leads comes out, and it pushes the body in this direction. So there will be the motion, and this displacement takes place xt, and here is the torque and theta t. So these are the three example of the translational motion, combinational motion, and the linear motion. You can see simply in the in a motor car where there is a motor moves around, and then the linear motion takes place in the our automobile. And Translational motion also, the you can see the wheel that is translationally moving along its axis. So in our automobile, you can see the rotational as well as the translational motion. So this way, this part is completed. And how this displacement takes place, you can see. So if the pinion is moving a distance, and that distance is represented by 2 pi r, so circumference. So, so that will be displacement of the motion. So that is represented as a capital L, and this capital is defined as a lead of a screw. So it is defined as a lead of a screw, and definition of the lead of a screw is a linear displacement that a mass travels per revolution of a screw. So it is a linear displacement of a mass per revolution of the screw. So here you can see J is a moment of inertia. So mr square rw by g. R here from this equation, R is L by 2 pi. So putting in place of R, you can put the L by 2 pi whole square. So this way it is the expression for the inertia in term of the lead of the screw. So we can review that in a mechanical system. There are two type of the motion. First one is a translational motion, second one is a rotational motion. In a translational motion, the body moves in a straight line. In a rotational motion, it takes place in the along its axis, fixed axis. So if any movement takes place, there will be the force, retarding force, that are called friction, and due to the its mass, there will be also force that will oppose the applied force. And due to the spring, if there is a spring system, so that will also oppose to the its motion. So these applied force will be balanced by the mass, its spring force, and frictions. That frictions may be viscous friction, static friction, or Columbus friction. Similarly, in the translation motion, and so this way the mechanical system of the any system modeling has been done. So in the next lecture, we will see the modeling of the gears and electric circuits. Thank you very much.